Okay, your chapter begins with a discussion of momentum and impulse. The first thing to understand is that momentum is a vector, and it's computed by, for a particle of mass little m, it's computed by multiplying the mass times the velocity of the particle. So momentum and velocity point in the same direction. And the units are kilogram meters per second. Secondly, from Newton number 2, as shown in the book and as I discussed in class, momentum before and after for a particle, before and after a force acts on it, is related to the impulse of the force, and the impulse of the force is the time derivative of the force over the time that the force is acting. So t sub I to t sub f, integral of f of x, f of t dt. So if you imagine an f versus t plot to be made of the force, vertical axis is f, horizontal axis is t. F has some direction. I'm imagining that F is in the positive x direction here, but it could be more complicated than that. The geometric interpretation of J sub x is the area under the F versus T curve, and so the initial momentum of the particle plus the impulse acting on the particle is equal to the final momentum of the particle. So as we'll see when we get to conservation of momentum, if the j for whatever the system is 0, then momentum is conserved. So there's different ways of writing this equation. You could subtract pix from both sides and conclude that jx is equal to pfx minus pix, which is simply a statement that the change in momentum is equal to the impulse. I will most of the time suggest that you use this first one because it's conceptually the simplest. So let's take an example. Let's say, this is right out of the book now, you had a 150 gram baseball and it has a velocity of minus 20 meters per second before being hit by a bat. After being hit by the bat, the baseball has a velocity of plus 40 meters per second. So it changes direction. So let's say, imagine that the F versus T curve for the bat is this blue triangle shaped F versus T curve. And so in that case, what we're being asked to find is to find the maximum force exerted on the bat. In other words, what this F max is. Okay, so the overall idea here is we know that the change in momentum is related to the impulse, and the impulse is the area under the curve here. So so what we can do is, first of all, compute the change in momentum, which is the final momentum minus the initial momentum. So that's going to be 0.150 kilogram times the final velocity, 40 meters per second, minus the initial velocity, so that would be minus 20 meters per second, and that comes out to be 9 kilogram meters per second. That is equal to the impulse, and the impulse is the area under the curve, which is 1/2 the base times the height of this triangle here. So it's going to be 1/2 times 3 milliseconds, time is in milliseconds here, times the height, which is F max, and we can now solve F max and see that we have a 6,000 Newton maximum force here. The second question is what the average force is of the bat on the ball. And so in order to conceptualize that, what we do is we assume that the same force, constant force, acts for that same 3 milliseconds, and so clearly in order to have the same impulse as the original force, which must be true, the area under this rectangle then must be the same as the area under the triangle. And so using that fact, we can deduce that the F average is 3,000 newtons. And one thing to note here is that the Jx points in the same direction as delta Px. That always has to be true. That's based on this this equation right here.